So this is, as you can see then, analog photonic links kind of make they're sort of the perfect thing to hook up right to an antenna. And so if I go back to my receiver front ends, how would I hook this up? Well, obviously from the antenna I'd go right into my modulator, and from my photodetector into my first stage here, and that's what I show here and how things look in the spectrum. But what you really ought to do, you want to remote as much as you can from the antenna. So you'll notice I kind of redrew the photonic link. I bent it so that I put the minimum amount of stuff up at the antenna, and that's the modulator. I don't even need the optical source up there, because remember, if I'm only sending the light over hundreds of meters, it's hardly attenuated at all by the time it reaches the modulator. There's almost no performance difference between putting the source here and putting the source far away. And remember, we're trying to minimize how much stuff goes up at the antenna. So this is what's called antenna remoting using fiber optic links or analog photonics. You'll hear it said different ways. So later I'm going to get into how do you make this box, this dashed box, perform well, because everything else I'm going to talk about kind of rests on that foundation. If you can't get this working well, there's no point in doing the other things I'm going to talk about. And the very next thing I'm going to talk about is why not do some of these other things? These are the names of those other boxes that I introduced. Why not, as long as you're in the photonic domain, instead of just converting back to microwave with that photodetector, while you're in the optical domain, what about doing some of this other stuff, such as suppressing those strong interfering signals? And like I showed you, sometimes the strong interfering signals are the things we are transmitting elsewhere nearby, or it's called co-site interference that we're generating, like for instance on that ship. This is something my boss Charlie Cox invented that is a means of using what you already have to make the microwave photonic link to do interference suppression. So remember those boxes in my block diagram? There was the CW, there was the optical source, which I said is often a laser being operated in continuous wave mode. There's the high-speed photodetector at the other end. I don't show any fiber, I just show an optical path in blue here. And that optical path has to go through what we call a modulator. The most common type of modulator is the kind I'm showing notionally here, called a Mach-Zehnder interferometric modulator. You can see that the input optical field is split into two waveguides that come back together and therefore interfere. And if you've kept them in phase in the two arms, they come back together and they constructively interfere. But if there's a pi phase difference in the two arms, they destructively interfere. So we make these waveguides in an electro-optic, what we call an electro-optic material, or a material where the Pockels effect can be used, and the Pockels effect is that an electric field across the optical waveguide changes its refractive index. So if I put an electrical field on this waveguide to change this refractive index, and on this waveguide to change this refractive index, as long as there's a difference between the electrical field that create here and here, I'll get a difference. I'll get if there's a time-varying difference, that time-varying difference will be translated into a time-varying optical output. I tend to bias myself like halfway between constructive and destructive, and allow that time-varying difference to then modulate how far up and down that curve I am. So that's what the green signal, the signal of interest coming from the antenna, will do, because I'm modulating the speed of light here, but not here with that signal. So that will give me sensitivity to the green signal. But if I can take a reference copy of my co-site interferer, the one that I'm generating somewhere else on my ship, for instance, that I've got to be sending out, and I wish this antenna could somehow be blind to it, but it isn't, it's right in my band. If I put that signal here on this electrode, I'm doing the same thing to this optical waveguide as I am to this. And remember, this cares about the difference between what happens here and here. So the output, it's interferometry, so it's got like a sinusoidal shape to the transfer function. but it's the sign of the difference between what happens here. So the subtraction happens first. This can be 20 watts, this can be 20 watts. That subtracts to 0 before you take the sign. So the sign of 0 is 0. The sign, if there's a little difference, then the sign of that is going to have some nonlinearity as well. And that's the whole point of interference cancellation. You want to get rid of anything big before you encounter a nonlinearity, because the nonlinearity will cause saturation and loss of sensitivity to the small signal, which, remember, the ones we're looking for tend to be small, and that's the whole problem. So this is the use of a microwave photonic link, the CW laser modulator detector link, the very standard link, to do interference cancellation. Ignore the hexagon. I forgot to tell you about to ignore the hexagon. I'm going to explain in a minute why there's a hexagon around this whole thing. And I said there were 2 examples of doing interference cancellation using photonics. This is actually the second one my boss invented. His name's Charlie Cox, and his other invention, I forgot that there were words that I could have put up there to explain what I'm talking about, the fact that the reds cancel and the green doesn't. But he actually invented this other one first. This is where my interference signal is actually what I'm trying to transmit out of the same antenna as what I'm receiving. And very people try to do what's called simultaneous transmit-receive from the same antenna because it's a difficult problem. And the hardware that exists to do it has a hard time doing it. That hardware is usually called a circulator. And sometimes it's made with ferrites, and it's usually, the ports are numbered this way. You know, I put a transmit signal, a signal I want to transmit out of what I have at port 2, in this case the antenna, into port 1, and what I receive from port 2 comes out port 3, but what I put in port 1 is hopefully suppressed at port 3. That's called a circulator, and that's always the symbol for a circulator, the circle with the arrow in it. And that's where the hexagon comes from. We had to make up our own name for this because the IEEE has defined what a circulator is, and you have to be able to commutate the ports in a circulator. So, you know, if I instead wanted to use this port as my input, and this is my bidirectional one, and this is my output one, a circulator lets you do that. This thing does not, because anything you put into this port will not come out anywhere else. The photodetector does not generate light to be detected elsewhere. So we call this instead, do I have the name for it up there? Well, it's a transmit isolating photonic receiver, which spells out TIPREX, and that's the name of our product. Oh, there it is. Yeah, I did spell it out. So same kind of principle by which this works. The received signal only modulates light in this arm of the interferometer. But the transmit signal I've split in half so that it modulates both of these. And we have customers who love this, and then there's people who would never, ever consider using this because you'll notice the signal I have available here at the antenna has now been cut in half. So it's not a coincidence I showed a ship. The Navy is okay with this because they have power to burn down in the belly of the ship. The Air Force doesn't love this on their planes because every bit of DC power is kind of precious. So they don't want to throw away half of their power. One interesting other thing though you can do with this is that you can make this impedance that you hang off the end of this match very closely the impedance of the antenna. This is another reason why a lot of people don't do simultaneous transmit and receive. If the antenna isn't perfectly 50 ohms, or perfectly the same impedance as this port or this port, you get reflections back from it that now do modulate the light, you know, very, in our case, modulate the light, or in this case, do make it out to port 3 without having to modulate anything very efficiently, and that's bad. So both of these products will only work well if you're not doing those reflections, if you're suppressing those reflections somehow. In the case of the TIPREX, there's this fourth port that lets you do that because what you hang here can be made to mimic the impedance of what you have here so that anything that reflects also cancels. You don't have that option down here. So we've had a lot of people interested in this. And here's another reason why they're interested in it. These are the transmit-receive isolations that are available from some commercial circulators. I pulled them off the web. They tend to be about an octave wide in different frequency bands here. They tend to be at higher frequencies because the size of the thing scales with the RF wavelength, so below a few hundred megahertz, the things would have to get pretty darn big, so that they wouldn't have much of a market. And they tend to only get about 20 dB of return of port 1 to 3 isolation. This is our tip RICs with the hexagonal symbol. We do better than 40 dB up until this frequency, and then again almost better than 40 dB out to, I think this gets up to 38 or so, up at 6 gigahertz. This is for one design. We have other designs that don't start as low but go higher. It's 3 decades of bandwidth, and this is just a network analyzer scan of it. It's not like we're doing tunings in between the frequencies. You get all of this at once. So it's very, very broadband. And that tends to be the advantage photonics gives you, is that these microwave frequencies are a tiny percentage of the optical carrier frequency. So anything you do in the optical realm affects all those microwave frequencies equally and all at the same time, and that's what you're exploiting. So that was one thing that can be done with microwave photonics for these systems. A second thing, I mentioned phased arrays. In the early 90s when I was at GE, this is why GE hired me. They thought they were going to do all their phased array beam steering using photonics because they have very broadband arrays, and it's very hard to get like RF delay lines to perform very low, in a very low loss way and in a very frequency invariant way across these broad bandwidths. So this is a notional phased array of just 4 elements. You know, the ones at GE were hundreds of elements usually. And this is a transmitting as opposed to a receiving array, where I take one RF signal, and by applying different delays, you know, here there's no loop, here's 1, 2, and 3 loops to represent different delays that you put on. You're causing the wavefront to add up constructively in certain directions. And what people want to do, what's called true time delay phased array beamforming, they want to be able to like switch in and out different delay lengths in each of these arms so that you electronically steer this beam in different directions. And it works in the other direction too, in receive, you know, to point the array in certain directions to listen. And if your array is not a broadband array, you can approximate this with just phase shifters in each of these arms, because at any one frequency, you know, a phase shift is equivalent to a delay. But you know, over a broadband, you'll have what's called squint. Now at each frequency will point in a different direction, and real broadband array people hate that. We thought this would be a great market for microwave photonics. It turned out there are so few arrays that are so broadband that they need true time delay. So we didn't find a lot of customers for this. The other reason we didn't find customers for it is it just didn't turn out to be to play to photonics strong suits so much. This is the most kind of straightforward type of true time delay unit, you know, where there's a path into this arrangement of switches and out of it, and in between you're switching between, you know, 0 and 1 tau and 0 and 2 tau and 4 tau and so forth. And you know, these are what's called bits of time delay resolution. So this would be an n-bit time delay unit. The trouble with photonics is the switches, you'd have to choose between, well, do I want fast enough switches, which are kind of lossy, maybe 2.5 dB per switch, or am I okay with very slow switches that take like maybe a millisecond or so to switch, which you can do mechanically with MEMS or thermal optically. And neither of those are attractive solutions. So most true time delay beamforming work that was done in the early 90s, before people realized there's not much of a market for this, was done in ways to try to avoid the optical switch. And I won't spend too much time on this because, like I said, it hasn't been all that lucrative a thing to do. But there were some really clever ideas that came out of it. This was some work by Ron Esman and others at the Naval Research Lab, where he realized, well, there's all these different kinds of fiber out there too. And the telecom people chose 1550 nanometers not only as the wavelength, not only because the loss was so low there, but because they were able to engineer the dispersion in the fiber to be very low. Dispersion was what was often causing the length limitation, where the broader bandwidth of modulation they put on, they found, the lower ends of my band they're ahead of the higher ends of my band, or the other way around, so my broadband digital signals, the eye diagram's shrinking on me. So they made these really low dispersion fiber. They call it non-dispersive, but it has a little bit of dispersion. And yet there were people who wanted the dispersion to be able to do clever things. And these people bought some of that and arranged the output of one modulator to go to 7 different photodetectors in this example through different lengths of dispersive versus non-dispersive fiber. Depending on the wavelength of the light modulated, you'd get arrival times at the detectors that varied with that wavelength differently in each fiber. And so by tuning the laser, they were steering the beam, taking advantage of these different lengths of dispersive versus non-dispersive fiber. It kind of made a prism out of it, which was really clever. The other way that kind of inherently photonic things can be used is in channelization. The telecom field, again, invented what you could think of as a channelizer, but they call the wavelength division multiplexer. If you've got a broadband signal in your fiber, they figured out a way to incorporate these, what they call arrayed waveguide gratings, to separate that light in such a way that these frequencies of light go over here, these go over here, these go over here, and we'll put fiber ports there to separate out. And the same device would work in reverse. And this shows that conceptually. Like I said, I'm not using color to indicate red light, yellow light, and so forth. It's really all wavelengths of light up near 1550 nanometers that are not visible. But I'm using red to mean the longer ones and violet to mean the shortest ones, wavelengths. And in this case, I'm representing things as if they're a prism. There's actually a free space optical prism. It's not. It's what's called an arrayed waveguide grating, and these are different fiber inputs and outputs. This would actually be what 2 of these would look like back to back. This is a single. This is either this one or this one, and it's the same device that you just operate in or out. It's passive. It lets you separate channels very effectively. This is something very hard to do in the RF regime because those RF frequencies here are such tiny portions of the optical bandwidth that it's easier to do in the optical realm. And in a low-loss way. Typically, for instance, for an 8-way multiplexing, that's 2 to the 3rd, I'd only have half a dB times 3, or a dB and a half of loss. A very difficult thing to do in RF. You see ads for diplexers and things, and maybe here it sends 1 to 5 gigahertz over here, and 7 to 12 gigahertz over here, and between is kind of a mess. And even that's very hard to do, very hard thing to design. So